This video covers heat transfers and the first law of thermodynamics. Now, in our last video, we saw that heat is a transfer of energy from one substance to another. Its variable is Q, and its units are joules. Now, James Joule demonstrated that the energy of masses moving in mechanical energy, was equivalent to the energy of heat. So in this picture, we can see a mass attached to a pulley, attached to a rod, and then attached to some paddles. Now, gravity is going to act on this mass and make it start moving downward. So it has potential energy. It's going to convert that potential energy into kinetic energy. But as it does that, it's also going to cause this object to start rotating. That means these paddles are going to make the water move faster and faster. So as the water moves faster, the temperature rises, meaning that we are increasing the internal energy. So we proved that heat is just another form of energy. You know that from previous science classes, there are 3 different types of heat transfers: conduction, convection, and radiation. Now, radiation consists essentially of electromagnetic waves. These do not require a medium, meaning that they don't need anything to travel in. Convection involves fluids. You know from, again, previous experience that hot fluids rise and cold fluids sink. So in this picture, you see these molecules down at the bottom warming up, and they begin to rise. As they move further and further away from our heat source, they begin to cool down. So as they cool, they then begin to sink. And so you have this cycle happening here. Okay? They heat, they rise, they cool, then they sink. Well, conduction can be partially explained by atomic or molecular collisions. If you look at this example, you see a handle that's getting warmed up. Well, we know that solids have their atoms very close together, and as it gets hotter, these atoms begin to vibrate. Well, as these atoms vibrate, they start colliding with the atoms next to it, and eventually the vibrations start to move up the handle. But you can actually calculate how long it takes to heat up and the rate at which heat is traveling, which we'll do in a moment. These equations show you the rate of heat transfer. Capital H is going to represent rate of heat transfer in joules per second. K is thermal conductivity. Now, every substance has unique properties and transfers heat at different rates. We know that metals transfer heat at higher rates, and things like wood do not transfer heat very well. A will still be area in meters squared. Delta T is our change in temperature. Again, in this case, it can be left in Celsius. And L is length, thickness, that the heat moves through in meters. Now, it's important to recognize that H is a variable, not heat. In our previous problems, or in our previous video, when we were describing heat, we were talking about energy, which is Q. In this example, we are talking about the transfer of energy, which is joules per second heat. Now, heat is also K times area times our change in temperature over our length, L. So if we do have these 2 equations for heat transfer, then we can set them equal to each other, like we'll see in our next example. In this example, a frying pan made of aluminum sits on top of a burner on the stove. Assume heat is delivered evenly over the bottom surface of the pan. The pan has a radius of 10 centimeters and is 0.3 centimeters thick. When the stove is turned on, the top of the pan is 25 degrees Celsius and the bottom of the pan is at 200 degrees Celsius. How much heat transfers to the food every 10 seconds? So we can use our equation. H is equal to Q over T. And what we're trying to solve for is Q, the amount of heat that transfers, where T is 10 seconds. So we want to solve for Q. Now, we remember have another equation for H, which is K, A, delta T over L. So in this problem, K is the conductivity of aluminum, which is 240. So What I'm trying to do is solve for Q. So I can multiply by T, and I get Q is equal to K times area times change in temperature divided by L. So again, my conductivity is 240 for aluminum. If you ever need these values, I'll give them to you. The area, here we're talking about a circular bottom. So this is pi r squared. So our radius is 10 centimeters. I can put that in as 0.1 meters. And my change in temperature, it's going from 25 degrees Celsius to 200 degrees Celsius. All divided by length. In this case, it is 0.003 meters long or thick. And you are multiplying it by 10 seconds. So the amount of energy transferred in that time is 4.4 times 10 to the 5th joules. This section is on the first law of thermodynamics. The first law states that the internal energy of a gas is affected by the amount of heat added to the gas and the amount of work done by the gas. Now, we saw this in our last video as well. Delta U is a change in internal energy. This is in joules. Q is a heat added to a gas, also in joules. W is the work done by the gas. This is going to be a very important distinction. Q is heat added to the gas, and W will be the work done by the gas. Now, the first law is a statement of conservation of energy. It applies to the system we are investigating. The system is the gas molecules and only the gas molecules. So delta U is the energy change of the system. Everything else, in this case we're going to talk about cylinders and pistons, is part of the environment. So Q and W is energy that moves between the system and the environment, the exchange of energy between the two. We saw in our last video that if we add heat to a system, then what we're doing is increasing the temperature, therefore increasing the internal energy. If we take heat away from the system, then we decrease the temperature, meaning that we are decreasing the change in internal energy. So this part you don't need to write down. We're going to see a summary of it in just a bit. Now, work is a little harder to describe. Now I want you to look at this picture. This blue block right here, this is going to represent a movable piston. What that means is this blue bar can move back and forth, meaning that we can change the volume of this container. So let's say that a force comes in and presses down on this blue bar, therefore decreasing the volume. If we decrease the volume, then we have to increase the pressure. If we increase the pressure, then we're increasing the temperature. So what we did is we did work on the gas. So work on the gas is positive work, meaning that we have increased the internal energy. Now, let's say that the gas itself does work. By that, it means that when we let this piston go after we've already compressed it, now this piston is allowed to move. And what the gas is going to do is start pushing it outward. So as it pushes it outward, the volume is going to increase. As that volume increases, the pressure is going to drop. If the pressure drops, then the temperature will also drop. So this is work done by the gas, and this is considered negative work because it lowers the internal energy of our fluid. Also, if no volume changes occur, well then no work is done and there is no change in internal energy. So this you can include in your notes. This is a summary of everything we just talked about. In this example, you have a gas that expands by doing 120 joules of work. So here, some key words is that we are expanding, and the gas itself is doing the work. So we are going to have a negative work done by the gas. During this process, 30 joules of heat are removed. Again, we're losing internal energy. So we have a negative 30 there as well. What we're asked is to determine the change in internal energy. Well, if we've lost heat and work was done by the gas, then both of these are negatives are going to add up, and we're left with negative 150 joules of change in internal energy. In this example, we have work done on a system. Is 450 joules, while the internal energy decreases by 260 joules. So in order for us to have a decrease in internal energy, even though work was done on it, that means that we have to remove heat from our system. So if we look at our equation and rearrange it, meaning we want to get Q by itself, then we get delta U minus work done by our gas is equal to heat. Again, here we have our decrease in internal energy, which is negative 260, minus the work done by the gas, and there is no work done by the gas. There's work done on the gas, so this is a positive 450 joules, gives us a negative 710 joules of heat that we need to remove in order to achieve this decrease of 260 joules. And our last topic for this video is the second law of thermodynamics. The second law of thermodynamics says that the natural direction of heat flow is from high temperature to low temperature. In the process, work can be done. So heat transfers from high temperature to low temperature, and work is done by the system in the process. So if this is true, again, we have negative work done. So while the natural tendency is high to low, heat can be made to flow in the opposite direction, just as water can be pumped uphill. Now, in order for this to happen, in order to have heat flow backwards, energy must be added, and work must be done on the system in order to achieve that. So we have two different mechanisms to do this. This one is called a heat engine, a device that uses high energy input to perform work while exhausting low energy. And a heat pump, a device that takes in a low energy input and uses work to produce a high energy output. Now we're going to see a diagram with all these signs, so it'll make a little bit more sense in just a moment. So let's look first at a very simple engine. Now this engine consists of a cylinder, closed on the left and open on the right, a movable piston, which is represented by this green bar in the center, a trapped gas, in this case those red dots. The system is a trapped gas molecules with internal energy U. Air outside the cylinder, in this case those blue dots, is part of the environment. Now heat reservoirs, something we saw in our last video, also come from the environment, and it will touch the left side of this engine. Now let's say that you have a hot reservoir. Again, this is something that can give a lot of heat, but it doesn't lose a lot of internal energy itself. So this hot reservoir is placed next to this cylinder, and we're going to see the transfer of energy go from the very hot reservoir to our compressed air. When that happens, we're going to see that this air is going to start moving faster and faster. So that temperature increase is going to increase our pressure. If we have an increase in pressure, then the volume is going to expand. So what it's going to do is it's the air on the inside, these red dots are going to push out on this green cylinder, and there will be work done by this system. Remember, as the piston moves outward, the gas loses energy, so the work is negative. Now, a cold reservoir does pretty much the same thing, but in reverse. Again, what a cold reservoir is, it's a very cold object that when placed up against another object, it takes heat from it, but it's so cold that its internal energy itself does not change. Again, this cold reservoir is placed up against our cylinder, It's going to start to cool down those molecules inside that cylinder, and it's going to start decreasing that internal energy. Now, as the temperature starts to drop, so will the pressure, and the volume of the gas is going to contract, meaning that this movable green piston is going to start moving to the left. So, as the piston moves inward, the gas gains energy. Again, this piston is compressing the gas, meaning that we're adding energy to the system. So the work is positive. So we'll stop here for now. In class, we're going to look at more of these types of diagrams and what it means in terms of the efficiency of engines.